Hi, and welcome to Test Prep for Test 8 for ENGPHYS 2P04 in 2018. We're going to look at the Test 7 from 2016, which matches up with the same material that we're going to do this time for Test 8. Okay, so this is on general elasticity, which is continuing on in the lecture notes past the flex PDE and shear stress and strain. Now we're looking at more complicated materials that can do more than just coupling the axial stress to the axial strain and the shear stress to the shear strain. First thing we do in general elasticity, as you saw in those notes, is kind of combine them all together into a single matrix. So we're going to look at how axial strain affects axial stress through the top part of this full Voigt notation 6x6 compliance matrix, and how axial strain is related to, or rather shear strain is related to shear stress through the bottom part here. And in addition, by putting it in this 6x6 matrix, we're going to be able to also calculate things for more complicated materials that do things like have non-zero components on this top in this top right corner, this top set of 9 elements here, which would be the ones that couple the shear strain to the axial stress, and then conversely the bottom left corner, which are the ones that couple the axial strain to the shear stress. And a little bit more mild than that, the ones that are off the main diagonal in this bottom right corner, which would be ones that couple one type of shear strain to another type of shear stress. The first question gives us this matrix, specifically a stiffness matrix. That's why it's in Pascal type units in this Voigt notation for some unknown material. And it asks us to figure out whether this is a matrix of an isotropic, non-isotropic, orthotropic, or general anisotropic. So I guess rather than just non-isotropic, I should say specifically cubic, but non-isotropic, which would be a type of material where this is all the same. So like this entry equals that entry, and then these three are equal, and then these three are equal. But unlike for a purely isotropic, we don't have that the shear modulus entries in the bottom right are equal to E over 2 times 1 plus nu, like they would normally be equal to. So you can get information on the crystal symmetry stuff when we, a little bit further in the notes just past the Voigt notation. That's where we have the write-up of all of those different things. So first we look at the pure isotropic setup and write out what the matrices would be for that. So here is your stiffness matrix for a purely isotropic setup. And you can see that there's this relationship between the bottom right components and the top left components, because G is defined through E over 2 times 1 plus nu for a purely isotropic. But for a cubic non-isotropic, we start to break that down. So there's a list of what the pure cubic single crystal materials behave like. So this is listing out what their actual G is, and then looking at the asymmetry, which is how far the actual G deviates from the predicted G based on E over 2 times 1 plus nu in a proportional sense. Okay, so basically this is just a set of write-ups on how you would deal with the different kinds of crystal symmetries that you could have. So if we have a pure setup where all of the components are equal and related by just these two components, E and nu, then that's perfectly isotropic. You could also have something where it has the same format, but the C44s are not the same as you would predict through E over 2 1 plus nu. And moving on further from that, a more anisotropic case would be where this is different in different directions, and that would be orthotropic in general, or transversely orthotropic, which is only different in some of the different directions. So like the X and Y are still symmetric, but then the Z ends up being different. And then further than that, we have the least kind of symmetry, which we're just going to call anisotropic, and this is a setup where you have things off the main diagonal. You can actually have shear coupling to other components of shear in the bottom right, and you have components in the top right corner. And because it's all symmetric, those would also be repeated in the bottom left, which would be shear coupling to axial things. Now, you're always going to have components off the main diagonal in the top left, but here we're really talking about off the main diagonal besides that. So for this one, right away, because you've got these components up here, this is anisotropic. Next, they say figure out the material's compliance matrix in Voigt notation. And the compliance matrix is just the inverse of the stiffness matrix. So we can get our computer algebra system here and compute the inverse of this matrix. So this is the stiffness. So we're going to call that C. Matrix 80, 20, 20, 0. Let's put this down on that line, actually. 80, 20, 20, 0, 0, 0. 21, 20, 30, 0, 40, 0. 20, 30, 80, 0, negative 50, and 0. 0, 0, 0. 50, 0, 0. 0, 40, negative 50, 0, 80, 0. And 0, 0, 0, 0, 0, 50. Okay, so let's see. Double check that that looks all correct. And it seems pretty good. Okay, so this is supposed to be in gigapascals. We can just remember that it's in gigapascals right now, and then get the inverse of this and remember that it's going to be in inverse of gigapascals. So that would be nano, so 1 over 10 to the 9 pascals would be nanometers per meter pascal. So that would be S is equal to matrix inverse of C, I think is the command. Yeah, okay, so we've got this set up, and if you like, you can evaluate it as a floating point to get it into decimal numbers. So depending on the zoom level that you've got in Maple, I just use Control-1 to zoom out. You might be able to see all of the different decimals or not, and you can also go in and set the precision to be different as well. So we can express this in, we can sort of force this to be more in an SI unit notation by first putting this into regular Pascal units, and then this compliance matrix would be in regular inverse pascals. So this is going to be really hard to read in this scientific notation because of the massive number of decimal points that Maple's showing by default in this precision. There's ways to change these. There's ways to change these things in the options. So the next part. Suppose that the cube is fixed in Z on its Z equals 0 surface and subjected to enough axial stress on its Z face to cause it to develop a compressive strain of 10% in that direction. Use Maple to determine how much stress is needed to do this and what you expect all 6 components of strain to be as a result. Okay, so you can use Maple to set this up. First, let's look at where what the equations that we're going to use would be for this. So the initial setup of Voigt notation at the end reminds us about how the stress and strain are related. So the stiffness matrix multiplied by the strain is going to be equal to the stress vector, and then the stress vector left multiplied by the compliance matrix is going to give us the strain vector. In this particular question, they tell us that the cube is fixed in Z on its Z equals 0 surface and subjected to enough axial stress on its Z face to cause it to develop a compressive strain in that direction. So because they didn't tell us anything about the other surfaces being fixed, we're going to have to assume that the other surfaces are just free, which means that the strain in all of the directions is 0. We know that we want a strain in the Z direction of negative 10%, and we know that we want the stress in all the directions to be 0, but we don't know what the stress in Z is going to be to do this. So, okay, so if we go over to Maple here, then we can write out our state equation that we would like. So we know that most of the stresses are 0. So maybe it makes more sense to work with the compliance matrix this time. So we can say epsilon is equal to the S dot the compliant, the stress vector. So the stress vector would be sigma, and maybe we'll first say sigma is equal to vector sz. Sz goes in the third component. So 0, 0, sz, 0, 0, 0. And epsilon is equal to vector. Now, most of these are going to be unknown. Ex, Ey, Ez, which we want to be negative 0.1, 10%. And E YZ, EXZ, and EXY. So actually, these last three, it should be 2 times these, or we could just work with the engineering strains. And then the equation that we've got is this one here, all written out after multiplying the vector across. So by looking at this last set of equations, then we really have 6 different equations in sigma z and all of the strains in the different directions. So the maybe the more kind of general way to solve this would be to say equation set is equal to maybe we'll call this Hooke's law. Hooke's law is equal to that, and then equation set is going to be equal to, let's make a sequence of Hooke's law. Now, we're going to need the left side of the equation, left-hand side of Hooke's law, and we're going to take the first component of that, and we're going to set that equal to right-hand side Hooke's law, that first component as well. And we're going to say this sequence for n is equal to 1, 2, 6. Okay, so this should give us all of the different equations that we wrote out in this thing. So the left-hand side of this equation's first component is equal to the right-hand side of this equation's first component. Left-hand side of the equation's second component is equal to the right-hand side of the equation's second component, etc. And why we want all of that in a list is because unlike just giving this vector equation, the solve command can solve a list of equations. Okay, so here's the solution to that. We've got what all of the strains are, and we've got the stress. So the stress that makes this work should be negative 0.17 E10 pascals, and all of the strains that that result in the other directions are written down there. Okay. Now, did you really need to use Maple to do this? Well, no. I mean, the stress vector here is so sparse that you could, once you've got the compliance matrix, multiply it through and see that all of the strains are just going to be related to one stress at most, if they even have something in the third column. So a few of them don't. So that's the shear stress, the shear strains in the YZ and the XZ. So those ones don't have any component in that column. So that's why they ended up being 0. But the rest of them do, and then they're just equal to something multiplied by SZ. So you could take the one that's supposed to be 0.1 and use that to solve for SZ, and then sub that into the rest of them. And that's essentially all the solve equation is doing. But by writing it out in this expression, we'd be able to use the same code to deal with something that's a lot more general of a set of boundary conditions. Part D asks us to verify this using FlexPDE, so apply the stress that we found and check that the Z strain is correct. Okay, so you should probably have code ready to go for solving general elasticity problems by the time you go into any kind of a test. But let's look at how you would build this up from scratch. So we've got a new problem set up here. We're going to go into Cartesian 3. We're going to need variables for the displacements in all the different directions, so u, v, and w, and we're going to use the select n grid is equal to 5. Now in the definition section, we're going to need to set up the parameters at the beginning. So the what all of the coefficients of whatever matrix we're using are. We're not going to need an initial value section. So actually, let's just put in this. So we're going to need matrix components. Then we're going to need something to define the strains from the displacements. We're going to need to relate strains to stress through Hooke's law equations. And then the actual equations that we're going to get at the end are going to be the same as before. So for u, we're going to have that dx of the x stress plus dy of s xy plus dz of s xz is equal to 0. In v, dx of s xy plus dy of sy plus dz of s yz is equal to 0. And in w, dx of s xz plus dy of syz plus dz of sz is equal to 0. No constraints. We are going to need some extrusions. So I believe the command for this is extrusion. We're going to name the surface bottom z equals 0 to another surface top z equals lz. Then we're going to set up our boundaries. So I'm pretty sure that this is how you would deal with all of this. And then we can recall these surfaces, surface bottom, and set up things like load u equals 0, load v is 0, load w is 0, and surface top, same thing. Then in the regions, we're going to start at 0, 0, and then we're going to take lines around. So we're going to go line to lx 0, lx ly, and 0 ly with all lines every time. No time. We're not going to use a monitor section. And we are going to need, if we're writing a contour, we're going to need to say where we are specifying this contour. So before we put in any contour plots, let's just put in the deformation plot. So grid x plus mag times u, y plus mag times v, w plus mag times z plus mag times w. Yeah, so this is going to be the deformed shape plot. And we're going to need to set up what mag is and what we can use any magnification we like. Maybe we'll start with 1. Lx is 1, Ly is 1, Lz is 1. Okay, so first off, is all of this part correct? So is the setup for how to draw the boundaries correct? Is the extrusion part correct? Are the equations correct? Let's have a look at the lecture notes where we have solutions to this. So I would suggest that if you want to, that you try an approach like this most of the time, even if you can look something up. So what I tried to do here is a free recall, kind of thinking about the things and remembering what it was, and then going to write it down, and then we're going to go and check whether it was actually correct. So it forces you to think through what the answer is, and this recall practice is a fantastic way to actually learn something. It makes you think about it. So rather than just go look it up, even if you know where to look it up, try to recall what it is and then go and check whether you got it right. Okay. So first, the initial setup of drawing 3D geometries. So we've got under this Flex PDE note, creating geometries for 3D objects, surface bottom. Okay, yeah, nailed it. Got the boundary conditions listed out correctly for that. And so all is well. Okay, now the actual equations for the net force on a unit volume, those also looked correct, so we're all good for that. Okay, so continuing on, we can write out what the Hooke's law equations are. Hey guys, Future Minic here. Just going to interrupt the video to point out that I'm about to make a pretty big mistake in typing out the equations where I accidentally say GYZ twice instead of GXZ over on the over in the stress equations. And a student who I've gone and hidden the identity of was nice enough to point this out in a great email and explain that this mistake had happened. So what I'm going to do is include some annotations along the way. This actually led to a number of different differences in how the flex results disagree with Maple. So a number of differences between the flex results and the Maple, and also to the flex code taking a lot longer than it should have to complete the simulation. So at the end of this part of the video, I'm going to include an addendum where we make the correction and show how it works out differently. But the mistake is going to stay in the video to point out the kind of things that will happen if you put this if there's this kind of a mistake in there, if there's something wrong with the equations, and how this can lead to sort of subtle errors. So we're going to get what Sx, Sy, and Sz are. Sx is equal to, now this time, this is the thing that's going to be the most different in this section compared to before. This time we're going to be writing these things out using the Voigt notation setup. So these are all based on the stiffness matrix components and all of the strains. So what we'll do is, maybe I'll move that over a bit just so that we can see it a bit better. So Sx is equal to C11 times EX plus C12 times EY plus C13 times EZ plus, now I'm going to say C14, and I'm not going to call that 2 times EYZ, but I'm just going to call that GYZ. So we'll go right to the engineering strain, plus C15 times GXZ plus C16 times GYZ. Okay, now we're going to use a copy paste to get the rest of the matrix components going. So we're going to have YZ, YZ, XZ, and XY. And then over here, for the actual entries, we're going to go C1, 1, 2, 2, 3, 1, 4, 5, 6, and then same thing over here. 6, 5, 4, 3, 2, 1, 2, 3, 4, 5, 6. Okay, 6, 5, 4, 3, 2, 1. Okay, so there shouldn't be any way that we made a mistake there. I guess anything's possible. So as long as we were careful to type out one version of this correctly and then change the coefficients in a systematic way, we should have everything done correctly for that. Okay, so now how do we define these strains? Ex is equal to dx of u, ey is dy of v, and ez is equal to dz of w. Then gyz is equal to dx of, or rather dy of w plus dz of v. So we don't need the divided by 2 because we're using the engineering strain this time. Gxz is dx of w plus dz of u, and gxy is equal to dx of v plus dy of u. So there should be 2 for each of the different components, 2 w's, 2 u's, 2 v's, 2 dx's, 2 dz's, 2 dy's. Okay, so by symmetry, it looks like we got all that done correctly. Now, next thing to do is to type in the actual matrix component. So here we've got this all in terms of C11, 12, 13, etc. So we've got 36 entries to type in, but there's a way to save a bit of time on this. So one thing is, since you know it's always going to be symmetric, you can copy down some stuff you can copy down the notation that's going to force it all to be symmetric, which is this set of equations here. So from the matrix being symmetric, we can save ourselves that many entries, all the bottom part of the matrix. So this just asserts the symmetry, and now we just have to type in the top components of that matrix itself. Okay, so let's go to the particular problem that we've got. And this was the stiffness matrix. So that's the one we want to type in, not the compliance matrix. So we're good to go. C11 is equal to 80 E9. C12 is equal to 20 E9. C13 is equal to C12. C22. So the rest of them are equal to 0. C14 is 0. C15 is 0. C16 is 0. Okay, next row. C22 is 120. C23 is 30. C24 is 0. C25 is 40. C26 is 0. Next row. C33 is 80. C34 is 0. C35 is negative 50. C36 is 0. Next row. C44 is 50. C45 is 0. And C46 is 0. Next row. C55 is 80. C56 is 0. And final row, C66 is 50. Oops, I guess I need gigapascals for all of these. So let's just put down E9, 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 and E9. Okay, so is everything correct? 80, 50, negative 50 for the 3.5, 80 for the 3.3. Then we've got a 40, 30, 120, and a 20, 20, 80. Okay, everything looks good. So now we'll see if the code works. So, success. It does something. It didn't crash. It doesn't actually do anything right now because we set a load boundary condition of 0 on all the different surfaces. So this would be, you know, bottom surface, top surface. Those ones are pretty self-explanatory. We probably need to label the boundary conditions for the rest of these sections. So now we've got x is sweeping, but y is set at 0. So this would be the y equals 0 surface. And then we've got x holding still, x equals Lx. And then the next surface is going to be, so the one over this next change would be y equals Ly. And then we've got y sweeping while x is 0. So the x equals 0 surface. Okay, so we've created our code, and now we can figure out, now we can finally apply the boundary conditions. So this is maybe where you would have jumped to from last week. The last, I guess, I don't know, 12 minutes, 13 minutes that we were working on generating the FlexPDE code would be something that you should definitely go through once, but then once you've got it, you don't really need to change any of this stuff except typing in the actual matrix components for whatever stiffness matrix you're dealing with in the particular problem. Okay, so the cube is fixed in Z and subjected to enough axial stress on the Z face to cause it to get a compressive strain of 10%. We figured out what axial stress that is when we worked with the Maple solution to this problem. The analytical solution there told us that SZ is equal to negative 0.174 E10 pascals. So we can go into FlexPDE and apply that on the LZ surface. So what do we need? We need that the bottom surface is fixed in Z. So we're going to set that to a value in Z boundary condition, and the top surface has a load of negative 0.174 E10. Okay, or negative 1.74 E9 pascals. So with the rest of the surfaces being load 0, we can copy a load boundary condition and then apply that. So you don't actually have to type them out for the rest of the surfaces. If you don't change it, then it continues that on from whatever you last had. So now that we've typed this in there, it's going to apply load of u, v, and w equals 0 on all of the surfaces. Okay, so let's see how this goes. So this particular one took 15 seconds to solve, and now we've got this this deformed shape here, and it is kind of funky. It looks like it has actually strained by 10% in Z as promised, and seems fixed in Z on the bottom surface. So we've got all kinds of different strains inside. To figure out whether these match the maple strains, we can report them. So perhaps reporting them at the middle of the matrix, of the object rather, would be a good way to test this out. So what we can do is go and include a summary section at the end. Yeah, just benchmarked it again, 15 seconds to solve. So I'll just cut out those solving times to make the video a bit more watchable for you guys. Needs all the help we can get. So summary section, we've got report val, and we can put in the strains that we're looking for. So we can go EX, and then we just need to say where we want to report that. So let's go right in the middle, X over 2, Ly over 2, and Lz over 2. They're all actually equal to 1 in this case, but in general, that would be a better way to do it. So we're going to put in 6 of these statements, and we're going to say all of the different strains. So EY, EZ, GYZ, GXZ, and GXY. Okay, let's see what those are. Okay, that time only took 14 seconds. Things are getting better. Anyway, here's what we got for the strains reported at the center. So let's go and compare that to what we discovered with maple. So we figured out that EX was 0.012 and maple said 0.012. If I only read out that many decimals, then it looks like they're the same, but they had disagreements on exactly what they were past about the third significant figure. So EY was 0.057, and we got 0.053 for EY. So not quite the same. EZ is negative 0.1, and we didn't report that. We set it to negative 0.1. GYZ is 4E minus 3. And it looks like GYZ was actually just 0 according to maple, and same thing with GXY. We found 0 exactly using our analytic calculation, and in FlexPDE we found that it's not quite 0, but it is certainly smaller than the other ones involved by a fair bit. And GXY, Flex calculated 0.093, and maple calculated GXZ rather, 0.089. So that one is the probably the biggest difference one that we found. So quite a lot different than what we were expecting in that thing, but generally things were pretty close in Flex to what they were in maple. Was everything larger in magnitude? Yeah, things were generally larger in Flex than they were in maple. Neat. To give a clue about why the answers might be different in Flex versus maple, I've gone and recalculated the same things in Flex, but at a different point. So rather than at halfway through the cube, we've gone 80% towards the top right corner from the bottom left corner, and now you see that we've moved to different values. So rather than 0.012 strain in X, we've got 0.0117, and so essentially what this is saying is that the actual strains that developed in the cube under this loading condition are not actually 100% uniform in all of the different directions like we assumed when we did this maple calculation. So by fixing it in Z on the bottom and applying this uniform Z stress on the top, the resulting displacement in the cube does not actually create a completely uniform strain, not subjecting it to a completely uniform stress and strain set. Now the last part here asks if it's possible to apply the compressive strain boundary condition directly in Flex. And the answer is yes. Rather than applying this load boundary condition on that surface, we can go ahead and apply a value boundary condition on the top surface. So value W, because we have a 1 meter cube, to set a compressive strain of 10%, we need a displacement of negative 0.1. So allowing this to calculate, your calculation time may vary depending on the computer setup that you've got. So these particular calculations can take quite a long time. So so now we've gone and applied this strain directly. It's exactly 0.9 at the top surface instead of this sort of close to 0.9 thing. And now we can determine what the strains are. Again, this setup does not actually lead to a uniform amount of strain throughout the material. So we've got different strains on at one location within the object compared to another location within the object. So something that's changing, we should expect a uniform Z strain at the top surface and the bottom surface, but is the Z strain uniform throughout the interior? It looks like it does change slightly compared to this 80% through and this 50% through. Where do we have a lot of change? So let's look for one of the components that has a pretty big change. The most different thing from the calculation before was the XZ strain. So why don't we have a look at that? Let's take a cross section through the material, maybe vertically, or actually we can even do like a horizontal cross section. What does the XZ strain look like? To do these sorts of things, let's take contours. So we'll go contour. I think the syntax for this is GXZ. And then you need to say, I think, on Z, and then you can give a boundary. So Z equals LZ over 2, I think should work. Yeah, so if that was a syntax error, then it would have caught it before the code actually started. So what this should do after this is done is create a color map of what the XZ shear strain is across the center face. So so there we go. It looks like in the range of the shear strain, we're sort of all over the place between locally large and locally small amounts of shear strain on the E-2 scale. So things changing from negative 9.9 to negative 7.9, kind of like a 20% difference between the large parts and the small parts all across the center of the thing. So to recap, we've got some pretty strange deformations because of the properties of this particular crystal. So by compressing it in Z, due to all of these components that are off axis in its matrix, we've got compressions in Z being linked to shear things showing up. So the material doesn't just stay as a rectangular prism when you end up compressing it, but can have all kinds of crazy things show up with its particular shape. Okay, now let's finally go and this is future Minnick again. Let's finally go and correct the mistake that we made earlier. So we're going to replace these with XYs in the last component, and we've reverted to the version of the program where we are applying just the 0.174 E10 pascals of stress on the top surface. And now when we run the program, first of all, it only takes like 4 seconds instead of 15, so that resolves another red flag. It doesn't have this funky shape happening on the top, and we end up with values of the strains, which now match much more evenly what we calculated with Maple there. So just to put this in the just to compare these things here, we've got we've got EX is the same at one part of the thing as the other. All the strains seem like they're not changing across the object anymore. We've got GXZ was supposed to be negative 0.0888, and now we've got 0.08864 there. I'm not sure if you can see that. Maybe we'll make that a little bit larger. Okay, 0.08864, and that's all good. And then 0.05263 for EY, and we've got that one right there, 0.052526, and that's it. And we have E-10, E-9 for the YZ and the XZ. Another thing that showed up is now these plots across the material are just constant, so the contour maps don't even look like anything, because we just have a constant value of the strain across the object, since now it's in uniform strain. So fixing this problem with the code has fixed all kinds of issues that we had. We can go ahead and apply the negative 10% strain directly in FlexPDE and see how that version of it works out. Again, pretty quick. So again, pretty uniform strain, uniform stress at the top, and uniform values for the strain everywhere, and actually the same values for stress and strain as we had before. So everything all works out quite nicely in this version, where we don't make nearly as many mistakes. So the next part of this test explores this a little bit more analytically, explain the effect of a non-zero C14 component of the stiffness matrix and the S14 component of the compliance matrix. So if we go and look at the equations for these, a C14 is the component that links the YZ shear strain to an axial X shear axial X stress, an X axial stress, not a shear stress. So what this means is that if the object is moving in Y and Z, that would tend to increase the X stress the higher C14 is. So if C14 is positive, then a positive shear strain in YZ would end up having a positive being doing something that increases the tensile stress in X, and vice versa. If this is negative, then a negative shear strain in YZ would end up increasing the axial X stress. Now, in the compliance matrix, S14 does kind of the inverse of that. Like, it relates the stress in YZ, the YZ shear stress, to the axial X strain. So if you have a YZ shear stress applied, then it would cause a direct change in the length in the X direction, other things equal, through this compliance 1,4 component. Determine the crystal symmetry of a matrix. A certain material has the following stiffness matrix components, but unfortunately much of the matrix components have been lost to the sands of time. So we've got all these question marks, and who knows what was supposed to be written there. It's like we find this on a pyramid wall or something, and we need to figure out what the rest of the components are. So fortunately, the matrix is still going to be symmetric. So by looking across, you can figure out what goes in those question mark spots. So this has to be equal to the same as that, so that's a 1. These two have to be the same as those two, so those are 1s. And then here, looking across, we've just got 0, so 0, 0, 0 means that those two are 0, and then the rest of those things, this L shape would go into that L shape, so those are all 0s, as are these and that. So that tells you that we've got at least a cubic material, but the question is whether it's actually isotropic. So is it fully isotropic, or is it cubic non-isotropic? And the thing that's going to tell us about that is whether this is the right size compared to these components. So if we go back to our notes, then we can remember that in the stiffness matrix for an isotropic material, we should have that the 1,1 component related to the 1,1 component and the 1,2 components are related in a certain way to be able to get this 4, 4, 5, 5, and 6, 6 component. So comparing these guys together, you can see that if we took half of the 1,1 component and subtracted half of the 1,2 component, then we should get the 4,4 component, right? So let's just check. So that would be, that would still be working out for the thing in front. It would all be proportional to that. So the inside, it should all work out as equivalent to what we've got. So half of the 1,1 component minus half of the 1,2 component should be the 4,4 component if it's isotropic. And in this case, that would be 1.5 minus 0.5 would be 1 rather than 2. So this has twice the shear stiffness that it should if it was going to be isotropic. Therefore, it's cubic non-isotropic. Still cubic because these three are equal, and then these three are equal, and these three are equal. But the relationship between this one and the ones up here are not is not what it should be if it was going to be a completely isotropic material. Okay, thanks for watching.